So hello to everyone who watches in the recording. And today we're going to go to the second topic in our course. Last time, we remember we more or less introduced the idea of a state space, which was like a way to describe linear differential equations, something that you already have seen before. We, wanted to use this idea to eventually describe something that we are going to control. And that was pretty much it. Right? We understood that we can write those things in various ways, in particular, ODE of high order or state space. So first order ODE. Okay. Today we are going to start with concepts that specifically very important to control theory, right? So we'll move away from ODE course and towards control theory course. The first topic is stability. Stability is essentially something that we want on the most basic level from all our systems that we control. It's a very big concept. Often enough, we see it as the ultimate goal of control to achieve stability. It's not it's not maybe ultimate goal, but it is very important, to the point that it is like one of those things that you always ask yourself if the system is stable or not. So what is it? What is stability? Let's try to understand. So today we will try to understand what it is and how to compute it. All right. So before we can discuss what stability is, we need to understand one concept again from differential equations, and that is the idea of a node. Okay, a node. What is a node? Well, consider this differential equation. So first order differential equation, just for simplicity. X dot equals to f of x and t. Okay. So derivative of x is depends on the state and depends on time. Okay. Now let's say that x0 is such state that f of x0 and t is uniformly equal to 0. Okay. So again, x0 is such that when you substitute it into this f, it becomes 0. In other words, it means that it doesn't change, right? So notice, right? It becomes 0. X dot becomes 0. That x0 will be called node or critical point. What is the idea behind, even calling it various names? Node, critical point. Well, the idea is it is a special state. Why is it special? It is special because if the system is at this state, it's not going to leave it. Okay. If the system state of the system is exactly x0, it is always going to be x0 because the x at this point, x dot is equal to 0. Okay, that is the idea. So it is a state where dynamics stops, the system becomes static. We call it node or a critical point. All right.
May I ask a question?
Yes. Let's go ahead.
So we said that x dot in this case will be equal to 0. So this is the extremum of the function, right?
You can say so, yes. You can say so. You need to be careful though, of course, because extremum with respect to what? With respect to time, right?
Oh, okay. So is it important that it should be like if the first like the derivative is 0, it might be a saddle point. Is it like important in this case, or it doesn't matter?
It will be important later.
Meanings.
Yeah, it will be important later. How exactly it looks, it will be important later for sure. But
Okay.
but it is for it to be a node, it can be anything. So let me just, I guess, give you an example. So let's say dx dt equals to x. For this equation, x equals to 0 is a node. Okay. So for this equation, x equal to 0 is a node. Let me give another example. Let's say we have dx dt is equal to x squared, let's say minus 9. For this equation, x equal, if x is equal to what? I would give us a node x equal to what?
3 plus 3 and minus 3.
Yeah.
Oh wait.
Yeah, exactly. No, absolutely, exactly right. X plus 3, x minus 3, right? So you can see that those are examples of nodes. Okay. And it doesn't have to be so simple, like, for example, dx dt equals to cosine x. That would also have a node. By the way, what would be the node for this?
Pi over 2 plus pn.
Yep. Pi over 2 plus pi times n, where n is any natural number. Right. Exactly. So you can see nodes not difficult to imagine. The whole point is that a node makes derivative equal to 0, and then the system at this particular node, does not move, it becomes static. That is the whole point. So this can happen at higher order ODEs as well. I'm using first order ODE here because it is very clean. The derivative, like, I think everything is easy to understand here. For higher order ODEs, what you need to make sure is that nothing changes at node. So it is not only the highest order derivative that is equal to 0. It is all derivatives have to be equal to 0 for the state to not change. Okay. So that is the whole point. And of course, is easy in those examples because time doesn't enter into this equation. But you can imagine, you can imagine nodes in situations where time also is a part of the equation. All right. So this is a what a node, what we call a node, right? Such x that x dot is equal to 0 for first order ODE. Okay. Now, a node can be stable or unstable. Now that's the first time when we encounter this lingo. So let's see. The node x0 will be stable if and only if, and that is just a definition, if and only if, for any constant delta, there exists a constant epsilon such that x initial conditions on x being, within in a delta distance from x0, if that implies that x will not be further away from this initial x0 than epsilon. I think that is maybe slightly familiar, but still clunky. It's always clunky to say. But so let me repeat it a few times. So first, I will just read this. If x at the point 0, if x at the point 0 is minus this node x0, so x at point 0, that is one number. X0 is a different number, okay? So different states. This is initial conditions. This is a node. So if the initial condition minus the node, the distance between them is less than or equal to less than delta, then this you know, if this implies that for any subsequent x that you get by solving the differential equation from this initial point, right? So you solve this x of t, you get it by solving the differential equation forward. So for any t, this x will not be further away from the node than epsilon. If this implication exists, then it is stable. Okay. Okay. Well, I make it sound a little bit complicated again, so let me repeat it the third time. I will try to do it again differently a little bit. What we want to make sure is that there exists some epsilon, okay? Such epsilon that x does not go away from the node more than epsilon distance, okay? So let's just demonstrate it a little bit on the maybe a small example. So imagine this is your 2D plane. Your initial point is maybe here. Your node is maybe here. Okay, that is your node x1, x2 coordinates. That is your node. At this node, dynamics is 0. Okay, and you say, okay, we found such epsilon here. This is the unit, this is the circle with the radius epsilon, okay? And we found such epsilon that x will never leave this circle. So any solutions, any possible solutions will stay within the circle as long as we start with initial conditions inside the delta circle. What is this delta circle? Oh, this is a delta circle. Okay. So stability is the property that we do not go to infinity. That is yet another way to say it. We don't go to infinity. We can always say that as long as we start in some initial region delta, we will not exceed some other region epsilon. Okay. So in this case, if we start in this pink area, we're not going to exceed this orange area. We're not going to go outside of the orange area. Okay. That is the idea. That is the idea. Okay. Okay. In other words, yet like first way to say it is the solution starting from delta-sized ball do not diverge, so don't go away. This all may sound a little bit mysterious. So let me just give some physical example that I think illustrates it quite well. So let's say we have here a mass on a spring. Bear with me while drawing the spring. Is not as fast as we would have wished. Okay. Okay. So you can imagine if the initial position of the mass, then here I'm simplifying. So don't take it like I'm like rigorous definition is at the slide. What I'm drawing right now is kind of like intuition. So let's say initial conditions of the position of this mass are, let's say, between here and here. Sorry, let me draw it in pink so we can see the connection between what I draw there. So let me draw it in pink. So let's say the initial condition for position of this mass here. So the mass will start somewhere in this pink region, okay? The mass will start somewhere in this pink region. And what we can say is that the mass will never leave the boundaries that I draw in orange. Okay, that is the idea of stability. I think this one maybe is quite clear. At least it is easy to understand what I'm trying to say. The mass can start anywhere in this pink region. We can put it lower, higher, but somewhere there, right? And it will not go outside of the orange region. So it may kind of drop below the pink region, right? Gravity, etc. May pull it down, but it will not exceed the orange region. That is the whole point. The reason this picture is oversimplified is because I didn't say anything about velocity. But let's assume the initial velocity is also like bound, like it is, let's say, between like 0.01 to minus 0.01, something like this. So in this case, we can say, yeah, the mass will not exceed those boundaries. So it is stable. So this system would be stable. Okay. Does this make any sense, what we discussed on the slide?
Yes, it's clear.
Okay. I apologize if it was excessive. This concept somehow is extremely important. We test it, we use it for all our subsequent work. So somehow I have to make sure you understand. Okay, good. Now let us. Do you have any questions?
No.
Okay, then we'll move on. This was idea of stability. So this is what we call stability. Now let me move to the next concept, which is quite as important, and that is asymptotic stability. That is a kind of like a higher order of stability. Like stability is a simpler thing. Asymptotic stability is more not, how should I put it, more strict condition. So let's see. The node x0 is called asymptotically stable if and only if for any constant delta it is true that what do we mean by sorry, I think it's not for any constant. If there exists a constant delta such that, sorry, there's not any, let me just for some constant delta, it is true that x of 0, so initial conditions, minus the position of the node, so the distance between initial conditions and the position of the node, being delta away, right? So again, it is exists some range of initial conditions that imply that x of t, as t goes to infinity, will tend towards the node. Okay. So as long as the initial point lies at most delta away from x0, trajectory x of t will asymptotically approach x0. Or yet another way, solutions starting from the delta-sized ball converge to the node. Here I can give another one of those visuals, but now with graphs, not with like not with physical examples. So let's see. All right. I'll draw two graphs. This will be my t-axis. So this will be my t-axis. This will be my x-axis. For now, we'll just consider a scalar case. So I have to draw now by hand, so apologies, it will be extremely ugly. My apologies. So if the system is marginally stable, so if the system is stable but not asymptotically stable, okay, it can, for example, be something like sine of x, or so like it can look like a sinusoid or something else. So how do I show it? Let's let's say something like this. Right. So is my attempt to draw a sinusoid. So from some range of initial conditions, it doesn't exceed a boundary. So remember, let me draw it in orange so we can remember what we were discussing previously. So from some range of initial conditions, the graph does not go outside of some boundary. Okay, that is stability. That is means the system is stable. Okay. Now, for asymptotic stability, what we require is that the system will go towards the node itself. So here, what we see is that the system approaches, I guess, zero, right? Zero approaches zero, and it approaches asymptotically. So as time goes to infinity, the value of x of t will be closer and closer to x node, x0, and eventually it will just be, they will be equal in the limit. In limit. So the difference between those two, between get rid of the seconds. All right. So the difference between, let's say, this and this is because the following: marginally stable system, so system like this, it doesn't have to converge to anything. The solution doesn't have to converge to anything. Okay, the solution can oscillate, or it can converge to something. Let's say another possibility, it converges to something, but doesn't converge to the node. So let's say it goes like this, and it kind of converges to some number, but doesn't converge to the node itself. Okay, so let's say the node is I will denote it by blue. Let me try to draw it. Let's say that the node is in both cases here, like at zero. If the system is stable, it doesn't imply that the solutions will converge to the node. Okay, so it doesn't imply anything about that. It only implies that they do not go into infinity, so they don't go somewhere away from the node. Okay, that is all that is implied there. Okay. On the other hand, for asymptotic stability, it is implied that the solutions will actually converge to the node. Okay. Okay. So that is the difference. In one case, solutions do not diverge. In another case, solutions converge. Okay. Well, that is two important options: do not diverge and converge. Okay. I apologize for being very slow with this, but that is kind of like key concepts going to be useful the whole time, and it's also a little bit difficult to understand, I think. Do you have any questions? All right, we'll assume that no, it means not. Well, let me show some examples. So here are a few examples that I think will illustrate what we're talking about. So consider this system, x dot equals to 0. Very simple first order ODE. So we can consider solution x equal to 7. X equals to 7 is a solution to the system. Why? Well, how do we check if any x is a solution to ODE? Differentiate it and substitute there, see if it becomes equality. And indeed, derivative of 7 is 0, so it is a solution. The solution is stable. By the way, notice that now I say solution. That is, in yet another conceptual leap. We can discuss it a little bit later, maybe. But this 0.7, this node, and because it is a node, it is stable. It is stable. Okay. Why? How do I know that it is stable? So let me again try to illustrate. How do I know that it is stable? That is quite important to be able to reason about simple systems like that. So let's just try to do this. So x equal to 7. Let's say here's 7. It's 0.7. Solution looks like this, right? Let me use the red for the solution. Here's solution x equal to 7. Okay, good. Now, how do we determine if the solution is stable or unstable? Well, let's say we get some delta region, right? I remember how we did it before. Some region delta. Let's say this region. Oopsies. Let me use some region like that, right? And we want to make sure that solutions that start in this region do not diverge somewhere, right? Do not diverge somewhere. Essentially, what we want to check all solutions that start in this region and see that they are contained in some epsilon region, right? How do those solutions behave? Well, they behave like this. They just go straight. So where a solution starts, where it continues, because x dot equals to 0. So all solutions to this equation look like lines, horizontal lines. They do not change. So you start with the initial conditions, you just continue. So those are all possible solutions to the example 1. And you can see that you can easily find orange region like this, for example, where solutions do not exit from the pink region of initial conditions. All solutions go straight. You can just pick a slightly bigger orange region. Done. You can see nothing diverges out of the orange region. The system is stable. Okay, good. But it is not asymptotically stable because nothing converges to the solution. The solution, again, is, remember, this red line here. This is the solution. Okay, nothing converges to the solution. So it is not asymptotically stable. Asymptotic stability is when you converge. Stability is when you do not diverge. So this situation, that's the situation that we have. Okay, let's consider.
So it means that if the solution, if there are a lot of solutions, it doesn't mean that they all have to be in one region. So for this equation, we have infinitively many solutions.
Exactly.
And the system is stable just because the derivative is 0, and not all solutions have to be in this delta segment, right?
So the delta segment is it talks about initial conditions. Okay. So delta is this, like you find some delta, like you need like some small ball. Why we say ball? Because delta is like the norm. Because we use norm. That's why we say the ball. Okay, we'll discuss later. But this delta region is distance from the node to the initial conditions. It determines the amount of initial conditions we are going to consider.
So we just suppose that x equal to 7 is initial condition.
No. Let me try to illustrate it, I guess. I mean, here's at the edge of the screen, it's difficult to see, but maybe we'll manage. So assume this is delta. So this is delta region, okay? Let's say in this case, delta is 2. So if delta is 2, you know, we can assume that, right? Let's say I will just write it here. Delta is equal to 2. Okay. Then this range will go from the node is equal to 7, you remember. So x0 is equal to 7. Okay. So that means that we're considering x from 9 to x equal to 5 here, right? So this is the edge of this pink region. So we have x's from 5 to 9 and everything in between. And we can easily verify that any solution that starts between 5 and 9 will continue to be equal to 5 and 9 because all of them are kind of horizontal lines. So what we observe here is that none of them diverge to infinity, for example. So if we pick epsilon, for example, equal to, let's say, 3, then like this orange region, just a little bigger than the pink region, nothing will escape it from the delta region. Okay, no solutions will escape it from the delta region. So we pick delta equal to 2, and we found that if epsilon is equal to 3, then the condition for stability is satisfied. So nothing from the delta region escapes the epsilon region. Nothing from the pink region escapes orange region. Good?
Yes.
But the way to determine it is, of course, is not easy, right? So you don't try to kind of like build mathematics yet. I will show it in a few slides how to determine all of this. For now, we just need to understand the difference between different stabilities. That is all. All right. Let me just try to show one more example. So next example is x dot equals to minus x. X dot equals to minus x. And solution is x equal to 0. Okay, solution is x equal to 0. This solution is stable and it is asymptotically stable. Okay, why? Well, you know, the solution to this equation would have the form. I don't know if you remember how. Can someone tell me what the solution will be? X of t equals to what? What is the solution, family of solutions to the differential equation? X dot equals to minus x. How do we solve this type of equation?
E in the power of minus x.
E to the power of what?
Minus x, minus t, minus t.
Minus t, exactly. Times c. Oops. Times t. Y times c. Y times c. Because initial conditions, right? The way the integration constant, right? The way we do it, for those of you who forgot, we say dx dt is equal to minus x. From this, we say that dx divided by x is equal to minus t. From this, we go to logarithm of x equals to minus t plus c, right? Something like this. And from this, we go to x is equal to exponent of minus t plus c. And from this, we go to x equals to exponent of minus t times exponent of c, which we can exponent of c, since c is just some integration constant, we can it is a constant at the point. We can always replace it with just some c1. Just for simplicity, I guess we put c1 here and we'll make it c here. And this is the same as putting c in front. So that is how we do it. This is the steps. Very standard. Okay. So the solution will be c times e to the power minus t. And e to the power minus t, as t goes to infinity, this number will very quickly approach 0. Okay, e to the power minus t will approach 0. Okay, c will be determined by the initial conditions. So at the point time t equal to 0, when t is equal to 0, this whole thing is equal to 1. So when t is equal to 0, this is equal to 1. So c is equal to the initial conditions. C is equal to the initial conditions, initial value of x. So given some initial region, let's say here I draw it in pink, any solution from this region will behave like this. It will asymptotically approach 0. So it kind of go like this. Any solution from this region will go kind of like this. Okay. They are not ever going to be equal to 0, but they will get very close to 0 very fast. So this is the example of asymptotically stable system. It is not only stable. Asymptotic stability implies stability, because if it converges, it definitely does not diverge. But moreover, whereas here you had things that are not even getting any closer to the solution, here things are getting close to the solution very fast. And yeah, indeed, this is an asymptotically stable system. Is that clear? Notice that for marginal stability is again is a way to say that the system is stable, but not necessarily asymptotically stable, right? So stability is a weaker condition, and we often say marginally stable to describe this type of situation. Right? This is a marginally stable. This is asymptotically stable. That is quite typical way to talk about it. Okay, so for marginal stability, notice we talk about this orange region, so the region from where we don't escape. With asymptotic stability, we don't need to think about it. We just go towards the solution. All right, last example. Consider the system x dot equals to x. You have solution x equal to 0. The solution is unstable. Why is it unstable? Well, the solution to this equation will be the same as the solution to this other equation. Oops. Let me try to get it. And it can be written as e to the power t, right? X of t is equal to c times e to the power t. Good. That is a solution, and it means it will e to the power t goes to infinity if the c is positive. If c is negative, it goes to minus infinity. So solutions in this case would behave. I will draw them in blue. Will behave like this. Okay. That's how solutions are going to behave. So they're going to go in all directions. None of them are going to stay inside any kind of region. We cannot find any orange regions that will contain all of those solutions because they go to like infinity. Okay. So in this case, the node c equals to x equal to 0 is unstable. It's not stable. It's not asymptotically stable. So first example, marginal stability does not diverge, does not converge. Second example, asymptotic stability converges. Last example, unstable diverges. Okay, just some examples. Okay, good. Any questions? Right. I'll try to go move on, and anyway, hopefully it will get clearer For now, I think the main question is how do you tell? How do you tell? Right, that is the main question, I think. All right, let us see how we can tell. How we can tell if the system is stable or unstable. It's actually going to be relatively simple. Relatively simple. Okay, so consider the following linear ODE. Is a familiar ODE, we already saw it before. X dot equals to AX plus BU. U is, remember, input. Okay. We call it linear time invariant system, or LTI. This indicates that A and B are constant matrices. LTI, this linear time invariant, is just useful thing to remember. You're going to mostly work with LTIs in this course. A little bit of something else at the end, but mostly LTIs. And but why do I bring it up? Because the machinery that I'm going to give you now works for LTI system. Okay, I'm going to discuss stability, and my discussion will be true for LTI systems, for systems where A and B matrices are time invariant, so constant. Okay. So now it's all nice, but since we don't know what U is, we cannot really say anything about stability. If maybe U will mess it up, right? We don't know. We don't know if solutions will converge, diverge, because we don't understand what U will do. Is input, right? It's outside of our knowledge or control. As in, if we decide what input is, of course, it's a different story. But in general, when input is just something, we cannot comment on stability. So let's get rid of input and consider the simplified version. X dot equals to AX. This is not only time invariant, so LTI. It's not only LTI, it is also autonomous. Autonomous. What do you mean autonomous? Autonomous, it means that it only depends on the state. It does not depend on time. So you can see, in order to compute X dot, you only need to know X. As long as you know X dot. There is nothing else that you need to know to compute X dot. That is what it means to be autonomous. In our physical world, we often like to think of things as autonomous. For example, let's say a planet orbits around a star. You would think that its velocity and its position is sufficient to understand its future velocities and positions, right? As long as we know like gravitational fields around those systems, right, and everything else like that. Yeah. Of course, in practice, this is a little bit simplified because we have multiple planets usually and other gravitational events happening. So you have to say, well, maybe one planet is not autonomous because other things happening, but the whole system, like the whole solar system, is autonomous, right? No positions, no velocities, and you will be able to simulate forward. Of course, then you would find out that there are asteroids and other things, so everything kind of like does a little bit of influence, and somehow it becomes, this concept breaks down. But you can kind of understand the idea behind it. If the system only depends on itself, does not depend on external events which change with time, only on its internal state, then it is autonomous. Okay, so the state is what describes the system, and if this is sufficient to determine all future history of the system, well, then it is autonomous. Makes sense somehow. Okay, and it kind of makes sense also that if we want to discuss stability, we want to work with autonomous systems, because if system depends on something external, how are we going to discuss stability? Good question. Okay, good. So when we talk about stability, we'll usually talk about LTI, so linear time invariant systems, and autonomous systems. So two things that we will look for. Okay. Any questions about that? It's just definitions. But okay. Now let us consider very simple autonomous LTI. Very simple autonomous LTI. X dot equals to dx. X dot equals to dx, where D is a diagonal matrix. Okay. Very simple, just a diagonal matrix. Well, this is actually the same as a system of independent first order equations. X1 dot is equals to D1, X1. X2 dot equals to D2, X2, etc. So what it is just a system of independent equations. X1 does not do anything to X2, X2 doesn't do anything to X1 or X3, and so on. They are completely independent. Each of those equations has an exact solution. Solution is X sub I of T is equal to C sub I, which is the initial conditions for this equation, times E to the power di T. Okay. So this is the exact solution for this equation. So if we want to discuss stability of the solution x equal to 0, and x equal to 0 for LTIs of this form is always a solution. Why? Because x equal to 0 is always, you can multiply by any matrix, so it still have 0. So x equal to 0 is a typical solution, is a typical node for linear systems. Okay. So x equal to 0 is a typical node for linear systems. All right. Now, what we have here is just the solution to this equation. And if we want to understand if x equal to 0 is stable, we need to see if anything diverges. And if we look carefully at what we have written here downstairs, let me emphasize it again. What we see is it can have only three possible behaviors. One, it can converge. And that would happen if D is less than 0. Then all those exponentials will converge. Second behavior, if D is equal to 0, then E times D times T, E to the power, sorry, of DT will be equal to 1, and the system will be marginally stable. It's not going to converge, not going to diverge. It is just going to be constant. That we have seen previously. If D is equal to 0, you can notice here it would just be like x1, for example, equal to x1 dot equal to 0. We studied it previously. So we already saw this situation on the previous slide. So if D is equal to 0, it's going to be marginally stable. Okay, going to not converge, not diverge. And finally, if D is positive, then this whole thing will diverge to infinity or minus infinity, and it is going to be unstable. So there are three possibilities. D bigger than 1, it diverges, so unstable. D less than 1, less than 0, it does not diverge. And if it is strictly less than 0, it converges. Okay, so from this we can argue about stability of the system. We can say it is asymptotically stable if all D, not just one, all D are less than or equal to 0. So we can say it is asymptotically stable if all D are less than 0, strictly less than 0. Okay. It is unstable if there exists D which is bigger than 0, then unstable. Then it is unstable. And it is marginally stable if all d's are less than or equal to 0, and there exists d that equal to 0. Okay. So we have, we have here divergence, convergence, and marginal stability. Okay. This may sound to you as if it is kind of like, who cares about this particular system? Why spend so much time on it? But everything that we will do, we will come back to the system. So that's why. Okay, so again, D negative, asymptotically stable. All D negative. All D have to be negative. At least one D positive, they're unstable. All D negative or 0, and at least one is 0, marginally stable. Okay. Marginally stable. So not asymptotically stable, but still stable. Okay. Any questions about this whole thing? All right. Let us now move towards more complicated things, and we'll see if this is useful. So consider now LTI with this form, where A can be decomposed via eigendecomposition, as A equals to V, D, V inverse, where D is diagonal matrix. And we assume that D is and V are both real matrices. So each entry is a real number. Notice not all matrices would have this decomposition. Can you tell me when matrices will not be will not have this decomposition? Someone tell me, please. When this decomposition is impossible. Again, I insist that D would be a real matrix of and V and D would have only real values. So can you tell me when this decomposition is impossible?
I don't remember exactly, but maybe when the eigenvalues are not real numbers or something like.
Complex doesn't have complex parts, right?
Yes.
Yep. For example, rotation matrices would have complex eigenvalues. Wouldn't be possible to decompose them. In fact, it is it is a subset of matrices which would have this decomposition. It's not typical. I mean, those matrices are not so rare, but yeah. Okay, good. But all symmetric matrices, for example, would have this decomposition. I think, right? I'm pretty sure. Okay, we can try to prove it. So this thing, so we just assume that A has this decomposition. We narrow the search towards those matrices. If this is true, then what we can do is we can rewrite this guy like this. Okay. Now, next step is multiply by V inverse equation 10. So we get V inverse here, we get V inverse here. Okay. So what happened is we have V inverse here, V inverse here. Okay. This is what we got. Right. Okay. Next step, we see that we can cancel some of the terms. This cancels V inverse times V is identity. Next, we will define new variable. We will get a new variable. The new variable will be Z equals to V inverse X. Just a definition. So VZ equals to X. And with that, what we get with this definition, we see that this is Z in Z dot. This is Z. And this is 1. So the solution becomes, the equation becomes this. So from here, we go to here with because of the decomposition and change of variables. But we know how to solve it. D is a diagonal matrix. And we just said that if all elements of D are negative, it is asymptotically stable. If at least one is positive, unstable. If all elements of D are non-positive, and at least one is 0, marginally stable. Okay. So we already know. So see, what we did previous slide, we use already on this slide. Good, good. But D are eigenvalues of the matrix. So it was eigendecomposition, right? It was eigendecomposition. So D are elements of eigenvalues of the matrix. So in this particular case, what we discovered is if the system's eigenvalues, which are real numbers, remember, we are discussing only the case when all eigenvalues are real. If system's eigenvalues are all negative, it is asymptotically stable. If system's eigenvalues, at least one of them is positive, it is unstable. If all eigenvalues are non-positive, at least one is equal to 0, then it is marginally stable. Okay? That is what we discovered on the slide. But that is only for systems for which this decomposition exists. Okay. So far, at least, we only proved it for those systems. But you see, it it kind of becomes very similar. For this system on the previous slide, this criteria would also work because this is clearly those elements are clearly eigenvalues of this matrix, right, of the system. Diagonal eigenvalues of a diagonal matrix are elements of on the diagonal. So okay. So far we have this eigenvalue criteria. Okay. Let's just consider one more type of matrix. That is upper triangle matrices. Upper triangle matrices. What is upper triangle? So essentially it means that anything below the diagonal is 0. Anything below the diagonal is 0. That is what it means to be upper triangle matrix. Okay. So for upper triangle matrices, the eigenvalues are the diagonal elements. So this is eigenvalues. Okay. Good. I don't know if you studied upper triangle matrices in your algebra course.
Yeah, we did.
Okay, good. Probably as part of how to solve systems of linear equations, I guess.
Yep.
Okay, great. So let us now try to see what we do with those. So let's say, again, autonomous LTI, where M is upper triangle matrix. Let's say all the eigenvalues are negative. All the eigenvalues are negative. Okay. And eigenvalues, again, are elements on the diagonal, remember. So it is elements on the diagonal. Now, the last equation of this system 12 looks like this. Xn dot equals to m and n, so the last eigenvalue, times xn. But since it is negative, we can observe that it is stable. This equation at least is stable. It tends towards 0 as time goes to infinity. Right? We already discussed it 3 times. So clear, this will be stable since this guy is less than 0. Okay. Good. Now, the equation before the last, so the previous equation, the almost the last, like penultimate equation, it looks like this. We have this x to the power, oh, sorry, xn minus 1 dot is equal to the penultimate eigenvalue and times xn minus 1. Okay. Plus this previously seen guy. How do I know this? How do I know what the equation will be like? Oh, it is a triangle matrix, remember, right? So what happens is you have, let me try to draw it somehow. You have elements of this matrix go kind of like this, right? Let's say 4 non-zero elements, then 3 non-zero elements, then 2 non-zero elements, then 1 non-zero element. Okay. So this is the last equation, right? The equation we discussed here is this equation. Okay. Then will be another equation, etc. So this is xn. This is like m and n, and this influences how xn behaves. Xn dot will be here somewhere, etc. So this is how I know this situation here. Okay, so let's consider this equation, the one before the last. So this equation, that's what we consider. The equation that has to do with the penultimate row. Okay. In this equation, what we can observe is that this component here will go to 0. Why? Oh, because this goes to 0, right? So as time goes to infinity, this component will go to 0. And what we are left with is this component, which looks exactly as this one here. It's stable first order ODE. Why stable? Because this guy is less than 1, less than 0, because all eigenvalues are negative here. Okay, so therefore this equation also tends to 0. Okay, and we can repeat this argument for all other equations going from the bottom to the top. We'll see that we'll see that first, let's say first this goes to 0. That means that all of those, let me show it somehow kind of like this. All of those make no difference. Then we show that these guys go to 0. So it means that all elements on top make no difference. Then you would show that this goes to 0. Then this makes no difference. And then ultimately you show that this goes to 0. That's how you kind of go. Very similar to Gaussian processes, etc. All those things. So for triangle matrices, what we see is, again, if all eigenvalues are negative, we have asymptotic stability. Okay. If at least one eigenvalue is positive, we have unstable system. Why? Well, because take any of those equations. You can take, let's say, this equation if you want, or this equation if you want, like any of those you can take. What you will find is as soon as eigenvalue here is positive, it blows up. And this one will blow up, obviously, right? We already studied it. This one will blow up because this component is still going to 0. And this component, if it blows up, nothing will stop it from blowing up. So we can easily prove that if one eigenvalue is positive, unstable. Marginal stability is also easy to prove in kind of like similar manner, but I'm not going to spend time on it. But so you see again the same picture. Eigenvalues determine stability. If negative, asymptotically stable. At least one positive, unstable. At least all non-positive, at least one zero, is marginally stable. Questions about that? You don't have to memorize this process, by the way. This is just to illustrate how we can deal with systems, and also to remind you about eigenvalues of upper triangle matrices. That might be useful on the tests. All right. Now, sounds good. Sounds good. All of this is nice. Now, let us consider this LTI system. And I apologize here, X probably shouldn't be bold. It should be just normal X. My apologies. It should be just normal. So this is a 2x2 system. Very simple. Eigenvalues of this matrix are not real. They're complex. It is a alpha plus minus I beta. So eigenvalues of the system are alpha plus or minus beta, I beta. Okay. So this is X, this is X dot. Okay. So how do we determine stability of the system? Well, we can claim that as long as dot product between X dot and X is negative, it will be stable. That is a strange claim, so let us justify it. Here it might be a little bit more difficult, so don't worry too much, but let's see if we can make sense of what we are doing. So if X dot times X is negative, so this is a dot product, okay? I claim that this would imply that the system is stable. How can do it? Well, we can decompose X dot into two parts, two different parts. One is parallel to X, so the component that runs the component that runs parallel to X. Okay, so it is co-directional to X, right? And another component that is perpendicular to X. So let me show it to you on the draw it for you. 1 second. I'll quickly make space. Okay. So it is two-dimensional case. So we have here x1, x2. Okay. So let's say we have our x as pointing here. This is x. This is vector x. Okay. And let's say we have our x dot to be equal to something like this. Okay, this is x dot. So x dot can be decomposed into two parts, as I said. One is parallel to x. Maybe just for simplicity, let me show x dot as pointing kind of like this, so it will be a little bit easier to draw. All right, now we can decompose it in two ways. One is parallel to x. This is a parallel to x part. Another one is perpendicular to x. This is a perpendicular to x part. And you can see now how decomposition works, right? Okay. So it somehow makes sense, right? We have this x dot being 2D vector, we can decompose it into two parts. One is parallel to x, one is perpendicular to x. Okay, good. Good. Now, so when we are going to have dot product of dot between x and dx, I will just dx dt, I will denote it as dx for now. This is the same as dot product of x with perpendicular component plus parallel component, right? Which is the same. Dot product, remember, is a linear function. So dot product of a sum is a sum of dot products, right? So we have x perp plus dot x par, right? So this is what we have. Right? Dot product, this dot product here, it becomes decomposed into like dx, x dot here is decomposed into perpendicular parallel component. And perpendicular component, dot product with something that is perpendicular to you, is by definition 0. So this is 0. Why? Because by definition of dot product, it is 0. All right. Okay. Dot product is, remember, by definition of being perpendicular, right? Perpendicular is what perpendicular vectors are vectors whose dot product are 0. But if you like cosines, you can think dot product is like norm of first times norm of second times cosine between them, and cosine will be 90 degrees, so 0. Okay. So what we see is that this thing here, only with this dot product here, only depends on the dot product between x and the parallel component of x dot. Parallel component of x dot. And from the picture, you can see here that this parallel component will drive x, will increase it in size or decrease it in size. So if their dot product is positive, it means that they are codirectional. So x will increase in size. Okay. Okay. If the dot product is negative, then this component will decrease x in size. Okay. So this is what this thing does. It increases or decreases x in size. What does this part do? What does this part do? X perp. Well, x perp only rotates the vector x. It doesn't increase its size. It only rotates it. So this green component, it only rotates x. It will change its orientation, but not magnitude. And what is stability? Stability is when we diverge or converge. So if our orientation changes, it doesn't influence our convergence or divergence. So that does matter. What matters is for us, in terms of going towards 0, what matters to us if we converge or diverge. And that only depends on whether or not this dot product here is positive or negative. So if it is negative, we converge to 0. If it is positive, we diverge to infinity. If it is 0, then we are marginally stable. So you see, this is where this condition comes from. This condition says, as long as this is negative, we are stable, asymptotically stable, in fact. If it is 0, marginally stable. If it is positive, we are unstable. So this is how we can argue. Any questions about that? Okay. Now let me show you. It's good. We got the criteria. Now let's see how it what has to do with eigenvalues. Well, let's compute this guy. This is the expression for this guy. How did we get it? Well, this is x dot. This is x dot. This is x. This is x. That's how we get it. Just substitute. And that's it. Very easy. Now, when we multiply it out, what we'll find is that beta will cancel. You can do it by yourself, but what you'll find is that beta cancels. And we are left with this expression. And let me again say, if this is 0, it is stable. If it is, if it is negative, it is stable, asymptotically stable. Positive, unstable. 0, marginally stable. But this guy can only be and we are talking about a range of initial conditions, not just some initial conditions, right? So what we find from this expression is that this part is always positive or 0, right? And it is 0 only at the origin. So we cannot depend on it to make us 0. So what happens is, if this guy is positive, we are unstable. If it is negative, we are asymptotically stable. If it is 0, we are marginally stable. And what is alpha? Alpha is real parts of the eigenvalues. Real parts of the eigenvalues. Okay. So what we found is that for this particular system, if the real parts of the eigenvalues are strictly negative, then the system is asymptotically stable. If the real parts are 0, the system is marginally stable. If they are positive, it is unstable. Good. Any questions about that? Any questions? Okay. Now, this system, we can write it as a vector field. What is a vector field? Well, that is, we write arrows like this for x1, x2. So we draw them as arrows, right? x1, x2 is a vector. And so those are coordinates where the vectors are located. So let me just show it as an example. So somewhere here is an x. It is this x, okay? From this x, we can draw an arrow like this. This arrow is this x dot, okay? So that's what we can do. And we can draw those arrows for all x's, and that is what we draw here. How do we interpret it? Well, how does x change over time? Well, it goes from here, and it changes in the direction of the arrows. So it will kind of go like this. Oh, sorry. Go like this, maybe. Like this, like this, like this, like this, like this. Etc. Right? We can plot the solutions. Like we can just solve the system using OD45 or ODint, and we will get the solutions. So this is a solution that we got. It started from here, it went kind of like this, right? So those phase portraits kind of allow us to analyze how solutions will work. Here we know that all solutions will spiral towards the center. Just from the phase portrait, we can see that they will always spiral. That is a nice thing about 2x2 systems. We can visualize them like that. Very popular thing in like just study. Any questions about this part? Notice that a real part of the eigenvalue tell you in which direction it will go. Since the real part is negative in this case, ultimately it's all goes towards 0, right? It converges. If the real parts were positive, it would have diverged. If they were 0, the solutions would always be perfect circles. So it would have the solutions would have looked kind of like this. they would have just started and then went in perfect circles. They would have just went around and around and around. Now, how fast it goes around, so how many windings it will get, that depends on the complex part of the eigenvalue. But that is not something we are going to study right now. You will hopefully have it on tutorial sometime. Okay, good. So this is a system, 2x2 system with complex eigenvalues. Now, just very quickly, I will show you something, how you can generalize this result. I will go very quickly because it's not something very important to memorize. It's just nice to see the connection. So consider the system x dot equals to ax, what we saw before, where a can be decomposed via eigendecomposition, again, into this thing, where C is a complex valued diagonal matrix and U is a complex valued invertible matrix. So we have eigendecomposition, but no longer with real numbers, now with complex numbers as well. That decomposition, as far as I know, and I didn't study it specifically, but as far as I know, it is extremely typical. Most matrices can be decomposed in this way. So this is actually very practical in this sense. Right. So we can multiply both sides again. So let me just repeat what we did before. We multiply both sides by a U inverse. So we multiply it here and here. Okay, by U inverse. It goes here and here. And then we can define Z as being U inverse minus 1. Sorry, U inverse times X. So we would have here like U inverse times X will become Z. And yeah. So after we did that, what we'll get is it's the same as we did before, right? Exactly same situation. So what we'll get is this equation. But this is again exactly the same as before. Is a system of diagonal equations. In each equation will look like this. So it is a system of scalar equations. The only difference is that they are complex now, because all of those are complex numbers. Complex number. Okay. Now, what do we do with those equations? All right, so far, this was exactly the same as with the real numbers, but the result is slightly different. Well, C sub I is alpha plus I beta, which, it's a complex number, so it has real part and complex part. And Z sub G is U plus IV. Again, complex number, real part, imaginary part. So, and by the way, I don't write G here just to make it less cluttered. Okay, now what we need to find is Z dot. What is Z dot? Sorry. We can expand Z dot, right, which is equal to those guys. Okay, so let me now try to illustrate again. So C sub G is this guy, right? And Z sub G is this guy. Okay, and we expand. So we expand this, right? And we expand this, right? So we just basically put the definitions. So we can write it out in terms of real and imaginary parts. When we open those brackets, and what is this? This is, of course, Z dot, which is U dot plus I V dot. Okay. So we've opened the brackets here, and we find all those elements, which are, let me now try to show. This is the real part. This is the real part, right? This guy. This is the imaginary part. This is the imaginary part. So this guy. Okay. Now we can like put imaginary parts here, right? What is the imaginary part? Well, it is beta times u, right? And it is a times alpha times v. So this and this, right? We can collect the real parts, which is u here. This is alpha times u minus beta times v. It is here and here. Okay. And notice what we got finally is that we have u and v times alpha beta minus beta alpha. That is the example that we saw before. We just solved it. And for this example, we know that solution is, it is stable asymptotically if alpha is less than 0, sorry. If it is marginally stable if alpha is 0, it is unstable if alpha is bigger than 0. So what we find is the criteria that for this type of problem, as long as all eigenvalues have negative real parts, asymptotically stable. At least one eigenvalue has real part is equal to 0. Everything else is non-positive, marginally stable. At least one eigenvalue has positive real part, unstable. That's it. That's it. Now, we did that only for systems which have this eigendecomposition. Complex, so it's very general, but only for those. And from that, we can basically, we skip a little bit and we just compose the general principle. I'll tell you what we skipped in a second. So for this general case, LTI, any A, so now we don't have any conditions on A, triangular, complex eigenvalues, real eigenvalues, anything, for any A, it is always true that it is stable if and only if eigenvalues are non-positive. It is asymptotically stable if and only if real parts of eigenvalues are negative. Okay, so all that we saw so far was true. It is eigenvalue criteria. To make sure the system is stable, we just need to make sure that the eigenvalues are not positive. To make sure it is asymptotically stable, we see that they are negative. What did we skip? What did we skip? Well, we skipped the traditional way to prove this statement here is by using Jordan block decomposition. So that is the most general way to talk about it. You provide decomposition to Jordan blocks. It is done almost the same as what we did with in the last slide. But the results are not going to be diagonal matrix with complex elements on the diagonal. It's going to be Jordan blocks. And what you can do with that is you can use the fact that Jordan block decomposition can be represented as a sum of two parts. Then you can do, for example, like matrix exponential, and there will be properties that allow you to decompose it into two components, one of which will, when you open it as a series, will like some elements starting from the nth element will go to 0. That is one of the properties of the Jordan block. And somehow through this matrix exponential together with Jordan decomposition, you can prove that again, same result will happen. So what will determine your stability will still be eigenvalues. The proof is not very difficult. It is just that like those eigen decompositions where, you know, we somehow can use them in practice and they're kind of close. Jordan decomposition is a little bit theoretical. So the procedure itself is unstable, etc. So it's not something that we encounter in practice very often. But in the suggested reading at the end of the lecture, I posted a link to a video where a person shows this proof exactly. So you can watch it. It's pretty interesting. So, but the logic I think is more cleanly seen through those particular examples. But this is a general result. This is a general result, and it is just always true for LTI systems, autonomous LTI systems. Okay. Now, I don't think we have a lot of time. How much time do we have, guys? 10 minutes?
We're 1
Minus
minute late.
minus 1 minute.
Ah, okay. So
Minus
we
1, yeah.
okay. So we don't. Okay, all we missed on this class is face portraits. I will discuss it a little bit. That is related this way to your question earlier about saddles, etc. Like saddles, you can even see them here. We will discuss those two slides in the beginning of the next lecture. But yeah, all we had to do, we did. Showed this criteria of stability. This is something you absolutely need to memorize, absolutely need to know. It will be on all tests, on midterm, everywhere in your homework. So take it seriously. All those things, that was for you to understand where it comes from. Those things, even people who do professional control sometimes forget how to derive those things. So it's useful, right? You can go through it. It is going to give you better kind of appreciation of what's going on. And in particular, even this quite random looking sequence here has something to do with Lyapunov stability, which is a cornerstone of nonlinear control. So, you know, none of this material that I presented here, I think, is without practical application. So if you have time, you know, go through those lectures, those slides carefully. It is not the proof for the sake of proof, is what I'm trying to say. All right, thank you for sticking to the end. Sorry, I took a little bit long today. Any questions? If no, then we'll see each other next week. Thank you, guys.
Thank you. Goodbye.
Thank you.
Goodbye.